Hi everyone, my name is Lam and this is my code explanation for task 8.1. In this presentation, I will focus on the solution in account management system built using object-oriented principle in CISO. So to begin, let me explain the overall solution and how it works. What you are seeing on this slide is the UML class diagram of my account management system. At the center of the design is the account class. This store each username and balance and expose methods like deposit and withdraw to manage those values safely. To handle banking operation, I defined an object-based class called the transaction. As so in the diagram, this class outlines a common structure for all transactions, which shared methods like execute and rollback. I then created three concrete subclasses: deposit transaction, withdraw transaction, and transfer transaction as well. Each of these inherits from the base transaction class and overrides the behavior and as needed. For example, the withdraw transaction checks for sufficient funds before processing, while the transfer transaction interacts with two accounts, both the sender and the receiver. All of these classes are designed to work together in a modular and extensible way, as you can also see from the relationship between classes in the diagram. So imagine that you are the customer using this system. You open up the banking app, right? Or in my case, the console menu, and choose an action like deposit or transfer. And right away, the system builds a matching transaction object for what you ask it. It sends that object to the bank class, which run the transaction and update your account. Behind the scene, everything you do, every transaction is saved into the list for tracking, auditing, or even reversing if needed. All of this happens smoothly without you needing to know how it's coding, and that's the power of clean object-oriented design. So now let's talk about the first principle, abstraction. Abstraction means hiding internal details and only showing what's essential. In my system, I use an abstract class called a transaction that defines a shared structure for all transactions, like execute and rollback, but doesn't provide the logic. Its subclass like deposit transaction or withdraw transaction implements these methods in its own way. This allows the program to handle all transactions through a common interface without needing to know their internal details. It keeps the system modular, consistent, and easier to extend. And now let's move on to the second principle, encapsulation. Encapsulation means hiding the internal data of a class and only allowing access through safe and public methods or properties. In my program, I apply encapsulation in both the account and transaction classes. For example, in account class, fields like balance and name are marked as private, meaning they cannot be accessed directly from outside. To interact with the account safely, I use public methods like deposit and withdraw, which include logic to validate the input before changing the balance. And similarly, in transaction class, fields like execute and datemestamp are declared protected or private. They are only accessible through read-only properties like execute and datemestamp, or modified inside methods like execute, which include internal check. This approach helps prevent accidental or unauthorized changes to the system data and ensure that everything stays consistent and secure. So now let's move on to inheritance. Inheritance allows us to create a new class that resumes the structure and behavior defined in an existing class. In my program, I implemented this principle by creating a base class named transaction. This class includes common fields such as amount and its defined object methods like execute and rollback, which every transaction type is expected to implement. After that, I developed three specific subclasses: deposit transaction, withdraw transaction, and transfer transaction. As you can see on the slide, a line like deposit transaction colons transaction means that deposit transaction inherits from the transaction base class. It automatically receives all the structure and functionality of the parent class, and then it overrides the execute method to implement its own deposit related logic. This design helps reduce code duplication and so that all transactions follow a consistent pattern and make it easier to add new transaction type in the future without requiring existing logic. So now let's talk about the final principle, polymorphism. Polymorphism means many forms. In programming, it's allowed to use the same command like execute on different kind of objects, and each one will behave in its own way. In my system, I created three types of transaction: deposit, withdraw, and transfer. Even though these are different, they all inherit from a shared class called a transaction. Because of this, I can store or own them in one single list, a list transaction. And then when I look through the list and call execute on each transaction, I don't need to worry about what kind it is. The program figures it out and runs the correct version of execute based on the actual type of the object. So if it's a deposit, it's add money, and if it's a withdrawal, I check the balance first, and if it's a transfer, it's move money between accounts. So this makes my cost much cleaner, avoid repetition, and allows me to easily add new transaction types later without changing the rest of the system.